theoretical work identifies hysteresis, the physical memory of a path, as the measurable shadow cast by persistence geometry. Finding this behavior in a laboratory is common, as countless materials inherently remember their structural history. General emergence mechanics approaches this search as a targeted phase sweep test. The theory predicts that this material memory will sharpen mathematically at one specific, predefined coordinate. The 255-degree protocol outlines the methodology required to isolate this geometric signature from ordinary material noise. Requiring the signature to appear at an exact location transforms the observation into a vulnerable, falsifiable test of the underlying mechanics. The primary search sector is defined as the 255-degree effective phase. This coordinate is a strict geometric requirement inherited from modal theory closure mechanics, serving as the predicted location of the geometric attractor. For systems utilizing a Z3 structural framework, researchers must also identify the secondary search coordinates. Because Z3 has a 120-degree sector spacing, the target shifts mathematically to additional points at 135 and 15 degrees. This provides the full array of sectors for the protocol: 15, 135, and 255 degrees. To physically test the theory, the laboratory only needs to execute controlled sweeps across these three specific coordinates. The experiment begins by identifying a controllable physical drive variable, x. This parameter can represent physical angle, polarization, torsion, or magnetic field direction. We then map this physical drive x onto an effective phase coordinate, theta effective. This mapping normalizes disparate physical systems into a unified geometric testing space. The Z3 search sectors are then located on this normalized phase axis. All subsequent physical measurements are plotted against this mapped phase coordinate. Mapping the drive to effective phase is the only way to locate the geometric targets and generate theoretically relevant data. The laboratory drives the physical system forward through the phase continuum and then returns it to the origin. By plotting the forward and return responses against the phase coordinate, we visualize the path-dependent loop. We calculate the total hysteresis loop area, h, integrating the response over one cycle. We then measure the loop width between transition points to define the memory window. We also record the relaxation time, which measures how quickly the system returns to baseline after the drive stops. Confirming these three metrics verifies that the physical sample possesses memory. While these metrics establish path dependence, the actual test for persistence geometry requires further analysis. Isolating the geometric signature requires applying derivative calculus to the response loop. Effective stiffness, the first derivative relative to phase, tracks the curve's changing slope. The primary metric is sharpening, the second derivative. A GEM-positive result is a localized, cusp-like peak exactly at the 255-degree target, whereas standard hysteretic materials show smooth curvature across this boundary. This localized curvature is the predicted shadow cast by the modal closure geometry. A localized sharpening feature at exactly 255 degrees indicates the precise point where the system alters its persistent state. A GEM-negative result occurs if no significant sharpening appears near the Z3 sectors, or if sharpening spikes occur at random intervals. Several material artifacts can mimic sharpening, including thermal changes, drive rate fatigue, and the accumulation of physical defects. If the sharpening tracks alongside temperature changes instead of phase boundaries, the result is disqualified. Laboratory controls must include sweeps away from the target sectors to establish a baseline. The protocol requires blank samples, variable drive amplitudes, and reversal direction tests to eliminate hardware bias. Checks for thermal lag and instrument drift are mandatory barriers for clean data. If the 255-degree peak fails to replicate across multiple different samples under these rigorous controls, the theory fails. Defining these conditions for failure makes general emergence mechanics a testable physical framework. Recommended systems for initial testing include ferroelectric materials, magnetoelastic systems, liquid crystal alignment cells, and chiral polymer films. The ultimate goal of this test is to verify if the defined geometric sector produces repeatable mathematical sharpening. This requires mapping the phase, calculating the second derivative, and surviving the rigorous control sweeps. This protocol bridges general emergence mechanics directly to the laboratory bench. It defines exactly what to sweep, what to measure, and where the shadow of persistence geometry must fall. If the persistent shell truly casts a measurable shadow, It should sharpen exactly where the fundamental geometry predicts.